Today we'll be proving Euler's identity. Euler's identity is the following. E to the power of I pi plus 1 equal to 0. So, in order for us to proceed, we have to see that e to the power of ix equals cosine x plus I sine x. We have to do a power series of e to the power of ix, cosine x, and I sine x. The power series of e to the power of ix equals to 1 plus ix over 1 factorial plus ix squared over 2 factorial, and so on. The following power series are the power series of cosine x and I sine x, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. And the same thing for I sine x, which is just I times x over 1 factorial minus I to x cubed over 3 factorial, and so on as well. By knowing these, we will now combine the power series of cosine and I sine, which will look something like this. Now we will simplify the powers for the power series of e to the power of ix. For that, we have to know that I to the power of 1 equals just I itself, I to the power of 2 equals to negative 1, I to the power of 3 is negative I, and I to the power of 4 is just 1. We will now rewrite e to the power of ix and compare it to cosine plus I sine x. We could see that once you simplify combination of the power series, it will look like the power series of e to the ix. They are highly similar. Notice that they are equal. Now that we have seen that e to the power of ix equals cosine x plus I sine x, to prove Euler's identity, we will substitute pi for x. As we can see, e to the power of I pi equals cosine pi plus I sine pi. For this, we have to know that cosine pi equals to negative 1, and I sine pi equals to I times 0. We'll now plug that in and get e to the power of I pi equals to negative 1 plus 0. And it's starting to look a little bit similar to Euler's identity. So all we have to do now is leave 0 by itself. The way by doing that is canceling this 1 and putting it to the left. So now we add 1 to both sides, making it e to the power of I pi plus 1 equals 0. We have just proved Euler's identity.